Hello. Okay, so welcome to the first video on Year 13 integration. So we're going to start by looking at a bunch of functions that you can integrate just by inspection. We don't need to use any fancy techniques. First, we're going to look at what I'm going to call the reverse chain rule. These are the first type. So if you think back to the chain rule, the chain rule was for when we can differentiate anything that is a function of a function, like that. So for example, we could do 4x squared plus 7 all to the power 18, because that's a function of a function, or e to the power of sine x or something. And we had a formulaic approach that would let us differentiate any of these functions or functions. Now, when we're doing this backwards and we're doing the opposite to that, the sort of inverse chain rule, well, it's not as powerful. We can't just integrate any function of a function. For instance, these two here, we can integrate them just using the chain rule, but backwards. Okay, and if you're wondering why that's the case, you could try it. Try and do. If you look at e to the sine x, if you do the chain rule backwards, you'll just integrate it and then divide by the derivative of the power, and you'll see that what you get doesn't differentiate to the original function. So that's what we're always wanting to think about. Okay, so this will only work when we are dealing with a function. Well, we've got a couple of types. Type 1 is when we've got a function of a linear function. Okay, so it's not as powerful, the chain rule in reverse, but if one of those functions is just linear, we can do it. Okay, so let's look at an example. So let's say we're trying to integrate 5x minus 2 all to the power 15 dx. So if we think about doing the chain rule backwards, we have to think of how we did the chain rule forwards. So when we did the chain rule forwards, we just we pretended, didn't we? Pretend the bracket is x. Pretend the bracket is just x, then differentiate. And then multiply by the derivative of the bracket. Okay. So when we do all that backwards, well, what we're going to do is pretend the bracket is just x. So that's step 1. Then instead of differentiating, we're going to integrate as if that bracket was just x. And then instead of multiplying by the derivative of the bracket, we will divide by the derivative of the bracket. So if we treat that bracket as if it's just x, that would be x to the 15. So we would add 1 to the power. And then divide by that new power. Okay. But now we've got to do step 3, which is now divide by the derivative of the bracket. Now, when we divide by the derivative of the bracket, the derivative is always going to be that number in front of x, because we are only doing this on linear functions. So we need to also divide by 5, which means we put a 5 underneath there. Okay. The other thing we're missing here is, because it's an indefinite integral, we need to put plus c. Okay, so that's just using the chain rule backwards. So that would become 1 over 80, 5x minus 12 to the 16 plus c. And one thing that we're going to get into the habit of doing, because differentiating is so formulaic, and once you've learned the product rule, you can differentiate any product of two functions, and once you've learned the chain rule, you can differentiate any function of a function. Since integration is less formulaic than that and doesn't always work as we'd like it to, it's a good habit to get into, to just check that when you differentiate your answer, you get the original function. So I'm not always going to do this check, but if we differentiate our answer there, what do we get? Well, this is a chain rule forwards because we're differentiating to get back. So we would treat that bracket as if it was just x. So we would get 16 over 80 times 5x minus 12 to the 15. And then we have to multiply by 5. And you can see there we get 80 over 80. So we get back to the function that we started with. So in general, with these sorts of integrations, that check is a really useful, method, just to make sure that you've got that fraction that's at the front correct. Okay. So let's look at another example. Okay, so this is a function of a function with one of the functions being linear. So let's go ahead and integrate this using the chain rule backwards. So we're going to treat the bracket there as if it's just x. So when we integrate e to the x, we get e to the x. So we just are left with 2x plus 5. But then we've got to differentiate the bracket and divide. So the derivative of that bracket is 2. So we get a half. Must put plus c as well because it was indefinite. Okay, let me give you a few to have a go at. See how you go. Okay, so pause the video, have a go at those 3, and then check, see how you did. Okay, so for question 1, we're going to treat this as if it's just x to the half, so it becomes x, our x, to the 3 over 2. We've got to add 1 to the power, and then we divide by that new power. So when we divide by 3 over 2, that's the same as timesing by 2 over 3. And now we need to divide by the coefficient of x. So we're dividing by 10, so we get a times 10 on the bottom there. Just tidy that up. We get 2 over 30, which is 1 over 15. Question 2. Treat this as if it's just sine x. So when we integrate sine, we get minus cos. So this becomes minus cos of 5x plus 4 plus c. And then we've got to divide by the derivative of that bracket, which is just 5. So we get a 5th in front there. Part 3. Treat it as if that power is just x. So we just get 5 e to the 4x plus 1. But then we've got to divide by the derivative of that power. So we divide by 4. Okay. So type 2. Now we can make our our inverse chain rule is pretty limited, isn't it? We can only, if I scroll back up, we can only use the chain rule backwards on things like this, where there's just a linear power, a linear function of x in the bracket. So it's a bit limited. We can do slightly better. And so if we have something like x squared plus 7 to the power 5, right? That function we can integrate using the chain rule backwards. But if we have in front of it something that is a multiple of the derivative of that bracket. So if I have a 2x in the front there, that we can integrate using the chain rule. Okay, so this will be things where we've got a function of a function, but then we've got the derivative of that middle function being multiplied in front. Okay, so it allows us to extend this chain rule a little bit. Okay, and the way we do that is we basically just integrate it, ignoring the product at the front, and then we just adjust it. Once we see what the function we come up with differentiates to. So let's look at this example. We'll integrate this. So the function that we're dealing with is x squared plus 7 to the 5. Now, because there's an x in front, it could be 2x, it could be 10x, it doesn't matter, as long as there's the power is like it's the same order as the derivative of that bracket, it should work. So what we do is we try the integral as we kind of would expect it to go. So that would be x squared plus 7 to the 6 over 6. So we try this. So you just ignore the product at the front, integrate it as you'd expect, and then we might just have to adjust the number that's at the front. So let's test it. If we were to differentiate what we got there, so if we differentiate this, we have to use the chain rule. And we multiply by the power there, so we get 6 over 6 times by the bracket to the power 5. And then we've got to multiply by the derivative of the bracket, so we're multiplying by 2x. So the 6 over 6 cancels, and we're just left with 2x, x squared plus 7 to the 5. Now that is exactly what we wanted. Okay, that is the same as the original function. Now that worked exactly right because that product at the front of the bracket was exactly the derivative of the bracket. If that happens, it will always work like this. But quite often, you don't have exactly the derivative of the bracket in front. So let's look at another example. Okay, so is this of the form we want? Well, what we've got is a function of a function, but the function inside the bracket is not linear. So this is not linear, so we are not going to be able to use chain rule backwards unless we've got the derivative of that bracket in front. Now, the derivative of the bracket is 6x, and we have x in front, right? So that's close enough. It's a multiple of the derivative. So what we do is we try just integrating this as if it was just x there. So we add 1 to the power and then divide by the new power. Okay. And now we need to adjust that. So we test this. So if we differentiate the answer that we've got there, which is 2/3 3x squared plus 7 to 3 over 2. What do we get? Well, we differentiate this using the chain rule. So we've got to multiply by the power and then subtract 1 from the power. So that gives us 2/3 times 3 over 2 times 3x squared plus 7. And we reduce the power by 1. And then we've got to multiply by the derivative. So that is 6x. So the 2/3 and 3 over 2 cancel. And we're just left with 6x, 3x squared plus 7 to the half. So that is 6 times too big. We've got almost what we started with, except it's got that 6 there. So I'll put brackets around this because this stage we are going to we're going to get to a point where we do this test in our heads. That's if we're writing this test out every time, this method isn't that straightforward enough. So anyway, we get then that the integral of x 3x squared plus 7 to the 1 over 2 is the answer that we got, which was 2/3 3x squared plus 7 to the 3 over 2, but we divide that by 6. So we get 2 over 3 times 6. And that simplifies to 1 over 9. Okay, and we can quickly check that again in our heads, just make sure we haven't made any arithmetical mistakes. If we differentiate that, we multiply the 9th by 3 over 2. So we get 3 over 18, which is 1 over 6. And then when that's multiplied by the derivative of the bracket 6x, the 6 will cancel. Let's try a couple more, and we'll try and speed up that testing step a little bit. So again, we need to check what's going on. So we've got a function of a function here, but the function inside the bracket is not linear. So, however, it's being multiplied by x squared, which is pretty much the same as the derivative of that bracket. So what we're going to do then is try we're going to just integrate sine x cubed as if it's just sine x. So it becomes minus cos of x cubed. So just as before, we don't have to divide by the derivative of the bracket. We just treat the bracket as if it's x. Now let's see if we can figure out what we need to divide by before we do the test. So if we differentiate that bracket, we get 3x squared. However, we only want 1x squared in front. So it feels like we probably should put a third there. Okay, so we can check by differentiating what we've got. So we use a chain rule here. So we differentiate minus a third cos. So that becomes plus a third sine. And then we multiply by the derivative of the bracket, which is 3x squared. Now we can see those those 3's cancel. And we're just left with x squared sine x cubed, which is exactly what we wanted. So again, let's put that check in brackets, because again, we're going to be doing that in our heads. And actually, that first guess was correct. We adjusted it correctly. Okay, next one. Let's try this. Have a go at this yourself before you watch me work through it. Okay, so again, let's have a look at this. So we need to. Obviously, all these examples are of the same sort, but when we're dealing with integration questions, half of the difficulty is deciding which technique to use. So we have to be able to train ourselves to spot, the type of integration we've got. So here we've got a function of a function. But the function inside the bracket is not linear, so we can't just immediately work out the answer. However, there is a product in front, which is the derivative of the bracket. So what we can do then is just treat that bracket to a half as if it's just x to the half. So we add 1 to the power and divide by that new power. And that's what we're going to try. Now we might need to adjust that 2/3. So before we do a check, let's see if we can figure out what that adjustment will be. Well, when I differentiate this bracket, I'm going to get minus sine x, but I've got plus sine x in front. So I haven't got exactly the derivative of the bracket in front. I've got minus the derivative of the bracket in front. So that suggests we're going to need to adjust this by putting a minus there. And if we're confident with that, we can stop there. But if we want to do a quick check, that's fine as well. Let's differentiate our answer and see if we get the thing we started with. So we differentiate this using the chain rule. So we get minus 2/3 multiplied by the power. Cos x plus 1 to the power minus 1. And then we've got to multiply by the derivative of that bracket, which is minus sine x. So the minus 2/3 times 3/2 times minus 1 all cancel out. And we're just left with sine x cos x plus 1 to the half, which is what we started with. So that's all correct. So now I'm going to give you an exercise to have a go at. Okay, so have a go at these 6 questions. Pause the video, and then I will show you the answers. Okay. Here are the answers. Okay, and let's have a look at those of the second type, where it's a function of a function, but we have a multiplier in the front. Okay, so here's the next exercise. I've deliberately gone to an older textbook that you've probably not seen, so that the most common Edexcel textbook. I did use the Edexcel textbook for the previous exercise, but I'm trying not to use those exercises as much as I can, because you probably have a copy of the official Edexcel textbook, so you'll have a lot more questions to practice that I don't have here. Now, pause the video and have a go at these. I'm not suggesting you do all 20 of these, but just do enough until you feel like you've got the hang of it. One thing to point out, what they've said for question 6 onwards, they've suggested using a substitution. So I'm telling you, don't use the substitution. In each of these cases, you have the derivative of the bracket in front, so you can just do it by inspection. I've left that, rather than chopping off the suggestion of doing a substitution, though, I've left it there just so that you can see this method of integration by inspection. If it is a little complicated to spot. Once you spot that you can do it by inspection, it's relatively straightforward. But if you don't spot it, it's not the end of the world, because all of these can be done using the method of substitution, which I'm going to cover in the next video on integration. So you have got a choice. If it doesn't sit right with you, this method of recognizing that you've got the derivative in front of the bracket, and then just kind of working out what would differentiate to give you that. If you find that isn't working for you, that's fine. You can use substitution, which will probably take a little longer, but it will work. And obviously substitution can be used on things that can't be done like this by inspection. Okay, so pause the video and then I will show you the answers. And here are the answers. Okay, so let me know in the comments if there's any of these answers that you're not sure about. I'm sort of experimented between on previous videos. I've worked through every question in the exercise, and I'm not sure which is more beneficial, for you to sit watching me work through every question, which could take a long time if you just want to know whether you got the answers right, or to do this displaying all the answers without working through it. So let me know in the comments whether you prefer to see worked solutions, and if there's anyone in particular you're not sure about. What's missing from these solutions, which you should have, is a plus C after every one of these. They are indefinite integrals. Obviously in the solutions they've just omitted the plus C. Okay. We're just going to look at one more type. This is a special case of the previous type. This is when we've got a function on the bottom and then the derivative of that function on top. That will always just be natural log of the denominator. Now, this actually is of the type we've already looked at. It's just it's just that this one crops up quite often, so it's worth spotting this in particular. So let's look at a couple of examples of this. Okay, so when we what we've got there is the derivative of the bottom is 2x. So we've got an x on the top. So we're definitely going to end up with natural log of x squared plus 7. Now, because we didn't have exactly the derivative of the denominator on the top, we're going to need to adjust this, and we'll need a half. We need to divide by that too. We can check that by differentiating. So if I differentiate, we use the chain rule. So we treat this bracket as if it's just x. So when you differentiate log of x, you get 1 over x. And there's a half there, isn't there, already? And now we've got to multiply by the derivative of that bracket. So we're multiplying by 2x. So here we have the 2's are going to cancel, and you're left with x over x squared plus 7. So that is correct. So that check is to just make sure we've got the right multiplier in front. Another example? Okay, so here we're using trig functions, and we've got the derivative of the bottom on the top. So this is actually a really quick way that we can integrate cot x. So this just becomes log of sine x. Now, that the numerator is precisely equal to the derivative of the bottom. So we're done. We don't need to multiply by a fraction or anything. So we've found that the derivative of cot x is log of sine x, which you can look in the formula book. That one is one that's given to you. And again here, if we differentiate that denominator, we get the numerator. So again, that is just log of the denominator. I should have that should be a modulus really for the bracket there. Okay, so let's have a let's finish this video by having a go at a few. Okay, so pause the video and have a go at all of these. And here are the answers. Okay, so you can see in every case, you just get log of the denominator. The only difference is occasionally we need to divide by the multiplier to make it work. So for example, for question 4, we have a minus 3 tan x on the bottom. So when we differentiate 1 minus 3 tan x, we get minus 3 sec squared x, which is minus 3 times bigger than the numerator. So that's why we have to divide by minus 3. Okay, so again, any of these questions in particular you want me to go through, put that in the comments and I will go through that. But for now, thank you, and tune into the next video where we will look at integration by substitution. See you later.